Alright, let's use the previous problem to prove this problem. And the previous problem basically said that we have a G invariant Hermitian inner product on V. So let rho from G to GLV be the given finite dimensional representation of G on V. All right. That's what when we say that V is a finite dimensional representation, that means that we have such a rho. Okay, so then, and rho here is of course a group homomorphism. Since V1 is a subrepresentation, V1 is G stable. Those two are equivalent. So by problem 8, V1 has a G invariant Hermitian inner product, and we'll call it just this inner product. Okay, so V contains V2, which we're going to define to be V1 perp, which is just a collection of vectors W and V, which are perpendicular to V1, i.e. for every single V in V1, the inner product of W with V is going to equal 0. Okay. Certainly V2 is a subspace of V. God. All right. Next, since this inner product is Hermitian, then we know that for every single non-zero vector V, the inner product of V with itself is greater than 0. In particular, there does not exist any V in V set minus 0 such that VW equals 0 for all W in V, because you just let W equal V itself, and you get a counterexample to this. Okay, so in other words, this inner product is non-degenerate. Basically, it's and any Hermitian inner product is non-degenerate. So, but I just decided to say it in a little more details here since it's something from linear algebra. Maybe you forgot about it. Also, it took like a sentence to prove. So, okay, so therefore, we know from linear algebra that V can be written as the direct sum of V1 and V2, i.e. V1 intersect V2 is trivial, and then every element of V can be written as a sum of an element of V1 and an element of V2. And this I'm not going to prove here because you should have seen a proof of this already in linear algebra, and also it's not a one-line proof. You do have to do a little bit of work here, but once you've done it once, it's fine. You basically do the whole Graham-Schmidt and you look at bases and things like that. So it works out. All right, so we will now prove that V2 is G invariant, i.e. for all let's see here, W in V2, and for all G and G, rho GW is going to be in V2. And of course this is equivalent to, for all W in V1, the inner product of rho GW with V is equal to 0. Okay, so let EI from I equals 1 to n be a basis for V1, and we're going to let Fj from j equals 1 to m be a basis for V2. Okay, fix G and G. Since V1 is G invariant, rho G of EI is going to be contained in V1 for all I between 1 and n. So let's fix some I between 1 and n and some j between 1 and m. Then Fj is going to be contained in V2, and thus rho G inverse of EI. Well, we know that. Okay, so no, that it's since this. These are two independent facts. We know Fj is in V2, and we know that rho of G inverse of EI is going to be in V1 because V1 is G stable. So since these two hold, we have so let's just go straight ahead to the calculation. So the rho G of rho G Fj inner product with EI is going to be, well, okay, this is a G invariant Hermitian inner product. And so what that means is that we can apply rho G inverse on to both coordinates of this inner product, and it's going to be this. It's going to give us the same thing. That's what it means to be a G invariant Hermitian inner product. Okay, so we have this, but then when we compose rho G inverse with rho G, they cancel out. And so we're going to have just Fg here, Fj there, I mean. That was a little weird. So we have Fj, and then we're still going to have rho G inverse of EI on the right here. But since Fj is in V2, that means that for every single element of V1, the inner product of Fj with that element is going to be 0, and rho G inverse EI in particular is in V1, and so this is going to be 0. See here. So since this holds for every single index between 1 and n, I between 1 and n, and since this Hermitian inner product is conjugate linear in the second coordinate, and that's just a basic fact that follows from the fact that it's linear in the first coordinate, but also it's if you flip the first and second coordinates, you introduce complex conjugates, and so you can use that to work out that if you take a linear combination of the second coordinate, you can pull the constants out with the typical linearity thing, but you end up getting complex conjugates on the constants. So what that means is that's conjugate linear in the second coordinate. So using those two facts, we have the inner product of rho G of Fj comma v is equal to 0 for every single v in v1. And that's because what you do is you take this element of v1 and you write it as a linear combination of the elements of the EIs. And then this is in the second coordinate, so then you break up this one Hermitian inner product into a sum of a whole bunch of Hermitian inner products using conjugate linearity in that second coordinate. And what you'll end up with is if you pull the constants that are corresponding to the EIs, if you pull those out of the second coordinate, then you're going to be left with just a sum of a whole bunch of terms where each term is some complex number times the inner product of rho g f j with some EI. And we know that that's going to be 0 because that previous thing that we proved that the inner product of rho g of fj with EI is 0. And so this is going to be a sum of a whole bunch of things which are 0, and thus the sum is going to be 0. Alright, so this holds for every single v1 and vi. So thus, this is what it means to say that rho g fj is in f2. Since this holds, that's weird. For all j between 1 and m, we know that rho g of w is in v2 for all w in v2. And that's because you take this element of v2, you know that it's going to be a linear combination of fj's. And then you use linearity in the first coordinate to take this linear combination of the fj's and break it into so if you take the inner product of rho g w with any v in v1, then it's going to be a sum of a whole bunch. It's going to be the inner product of a linear combination of rho g fj's. No, it's going to be the inner product of okay, you know what? Let's just write it out. Because rho g, so the for all v and v1, the inner product of rho g w with v is going to be the inner product of rho g of the sum over all i's of I goes from whatever to whatever else. Okay, so maybe it's j. It doesn't matter. It's going to be, let's say, aj, fj. This composed with v. And then, since rho g is linear, this becomes a sum j, aj, rho g, fj, v. But since this is a Hermitian inner product, it's linear in the first variable. And so this is going to be sum j, aj. And then here we're going to have the rho g, fj, v. And then here, this is just a sum of a whole bunch of zeros, and so it's 0. And so there you go. Alright, that's a lot easier than me trying to say that in words. The words might have been faster if I were to say them well, but I wasn't doing that. So anyway, so this is okay. So that's this. This holds for every single g and g. Hence, v2 is g stable. So we're pretty much done here. Finally, since rho 1 or v1 and v2 are both g invariant, we can define representations. Let's call it rho I from g to gl vi by rho I of g of v is going to equal rho g of v this will work for I equals 1 and 2. Let rho prime be the direct sum of these representations. Then for all v and v, we know that there exists unique v1 and v1 and also a unique v2 in v2 such that v equals v1 plus v2, and this holds since v is this direct sum. Alright, and then rho g of v is going to be precisely rho g of v1 plus v2, which is going to be rho g v1 plus rho g v2, which it turns out is rho 1 g v1 plus rho 2 g v2, which is going to be rho prime of v1, v2, and maybe there should be you know what, that like you do have to be a little careful here because of these we're sort of implicitly going from plus to direct sum, but I'm not going to worry too much about that because you kind of know what's going on here. You can sort of see what's happening. You could be a little a little more pedantic if you wanted to about when do we stop using plus and start using direct sum? When do you stop thinking of this as a sum of two things and start thinking of it as an ordered pair? I'm not going to get too much into that because we're basically done. And so thus rho is isomorphic to rho prime as representations. And in other words, we have v is isomorphic to v1 direct sum with v2 as representations. Alright, and that's exactly what we wanted to prove, and so we are now done with this exercise.